Our next presenter is Henrik Bang-Andreasen. Henrik has been in the industry for about 40 years. 30 years of that time he spent at Seaproof Solutions, which he also founded. And Seaproof Solutions was a company specialized in designing and manufacturing, amongst other things, cable protection systems. Has it not?
Well, it's too late to say no.
Yeah, but anyhow, it's been acquired not that long ago, and since then, Henrik has been a consultant for cables and cable protection, and recently founded Portunus Solutions. So, Henrik, over to you.
Okay. We were told just now, and I'm sorry that we're going to talk more about CPS systems, so I'm sorry I'm going to bore you more or make you feel even more lazy this afternoon. Unfortunately, I have more than 25 years of homework done, and some of it I will actually show you now. It was said here that one of the big things was like DNV 109 pipeline stability on seabed and whatever. In offshore wind, it's predominantly the ST 0359 and the recommended practice 360 for cables and so for offshore wind. That is the issue. The problem really is that it's what DNV have tried to do is they've tried to do a kind of EasyJet kind of way of doing the API 17, where you actually qualified the flexible, which could be a cable, of course, and the actual bent management system, bending strain relief and so, together in one system. And one of the big things, now I've been in quite a few projects, I believe one of the big problems lay in that there's just, they touch it rarely. I think there's 10 lines in those two standards and recommendations about the boundary conditions, as it's being called, about the cables. How to talk about the cable boundary conditions, which has to do with, for example, the CPS and what have you. So in the project, this is not being addressed, as a former speaker took it up lightly. It's a big problem, and now I'm going to show you what the problem looks like. Understanding the problem, I'm not going to spend too much time on this, but here, unfortunately, quite a few pictures. If we start on the left, it was meant that I was going to show you this in three things, but for some reason it comes all in once. But on the left-hand side, you see a CFD analysis of the current flow of one wave around 1 meter above the seabed around a monopile. So you have the white spot in the middle is the monopile. On the top you got, and that could very easily be a Seaproof CPS there, which is now Balmoral. And that's how the CPS suppliers and how I would like to present it. Orcaflex, for example, an even Orcaflex, and you will understand a little bit later why I say even Orcaflex, present what it's going to look like below. So that's actually the relaxed in the middle, and you see the thing tumbling around there, 3 meters to each side. So the thing that some of you may think that the CPS is able to actually keep, which you were addressing, maybe the CPS system cannot really do what we think it should do. It cannot keep the cable still. It cannot keep the cable frame. So what you must understand the system is today is that the CPS supplier is actually running an analysis trying to demonstrate that the curvature and tension pairs on his, because very often the cable supplier is not very cooperative, and therefore the CPS supplier have to do it alone on a very symptomatic cable design, where they actually go in and look at what is the typical fatigue life of the cable components for those curvatures and so. So what the CPS supplier is basically being asked for is, if we install the CPS this and this way, can we actually get a curvature and tension pair on the cable that allows the cable to actually survive for this many years? That would typically be 320 years for a typical 30-year project. You need a safety factor of 10, and you need typically 1 to 2 years to build the wind park. Doesn't take that long today, but that's the thing. And you need 2 years to bring it down. You need to have the cables working. You still need to have lights on the foundations when you demo up the foundations. That's a thing. So that's basically what's happening. So why on earth does it, after 2 years and 3 months, look like you see on the right-hand side top? For those of you who cannot see what that is, it's not my rack doll. It's actually a cable. It's a 66 kV cable that's been out there for 6 months. I've never said it, but it's a project in the UK, and you can see the CPS next to it, and you can see it's grinded down, and this is what the cable looks like on the inside. I can tell you on the other end of this cable, the cable looked the same, apart from only half the PE insulation on that conductor was actually, or I don't know if it's that conductor, but on the conductor, so only halfway through. And the cable was okay in the other end when it was tested, but still half the insulation was gone inside. So it's a big washing machine effect inside. And the thing is, of course, that most of the designers have made assumptions, and I'm coming back to this again. And if we were going to build offshore wind parks in swimming pools with chlorinated water, this would be a very good, excellent solution. Unfortunately, we decided to put it out in the real ocean, where we have something which is currents, we have many different things. I have looked at approximately 107 CPS failures in the North Sea alone, and they come in different shapes, and so I even seen sea-proof CPS systems failing. So it's not that I'm trying to point fingers at something different, because those failures that you see here is not that. But what you have is, you see here and here I use a Tecma system, and this Tecma CPS system is the same for CPS, for any system, whether you buy it from, there's 4 suppliers at the moment. You got Tecma, you got CRP, that's now AIS CRP, you got first Subsea, and I did say Tecma, didn't I? Balmoral. So those are the 4 that supplies at the moment. The big difference is, of course, for those who actually want to read and even put on their specification that they design their CPS system according to API 17, they should also note that API 17, I mean, you have to be really difficult not to understand when they write that you cannot use a bend restrictor in anything that's dynamic. So having bend restrictors, as you see here behind on the right-hand side of this black thing there, is fine as long as it doesn't move. So if there's no dynamics, this would be fine. But then, of course, there's other issues. And this comes from, you've got the mobility in the orange section, you've got the tension in the red long line, and this results in that you've got polymeric degradation, abrasion, and you've got metallic and iron corrosion and abrasion on the black part of it. So what is this? As said, the root cause is the mid-ocean. I'm going to tell you in a little while what the mid-ocean really is, to put some figures onto it. The symptom is the mobility, and therefore, of course, it's nice to go to a doctor when you get a headache and you get a pill against the headache. But it would be nicer if he, for example, fixed the hole you had in the head or something. So the thing is, what Ørsted did when they put on the stones, the rock, or René's Stone Age, can you tell me the rock, what did you call it? It wasn't installation, rock. Did you call it rock installation? The rock installation, of course, is that the actual stabilization by the weight of the rocks of the CPS should stop the mobility. That's really the symptom that's being stopped. It stopped this part that's actually from it touches the rock berm, stops that part from moving. So that cures the problem, is the idea. There's a few other things. You said it earlier. Modals, assumptions, all the small things that say, what are the assumptions? What are the modals? What do we put into the modals? And the big thing I can tell you today is, not surprisingly, when this CPS supplier have made the analysis, which very often he does not do himself. TechMark, for example, do it with Agile Tech, and other people do it with other companies. But when that's done, the client then ask for those models and say, well, can you demonstrate to us that the cable will actually survive to the end of the project life? That's what's happening. So what does the client then do? The client takes the same model they get from the supplier of the CPS with the same assumptions, with the same model, put that into their system, and guess what kind of result they get? Yes, everything the CPS supplier told us is exactly this way. The really stupid thing that happens is when the third party comes into the play, what does they do? What do they do? Surprise! Surprise! Any of you guess what they do? Well, they require from the client the model, the program, everything that was supplied by the CPS supplier, run the same thing and come out and say, yeah, it looks good. It's going to work for 32 years, no problem. So why do we have problems? Of course, there's a few issues where some people have been very creative, using start-of-life properties in materials and so we don't have this. No, this doesn't work. No, we don't have corrosion. No, we don't have sedimentation inside the CPS system. Of course we have sedimentation. When we pulled out all the cables that was going to be changed from the JDR inline fields issues on Hornsea 1, we pulled out 27 cables, did 27 offshore splices, and all of them was totally, this was sea-proof systems, they were totally filled with sediments. So this thing that people think, oh, inside the CPS system, the CPS can actually move around. It cannot. So that's kind of the problem, why the assumptions, why the models that is being put into the models are wrong. But the really big problem lies here. The really big problem is that if you look at the left-hand side, these two figures, 3.7 meter per second and 2.4 meter per second. I know I'm used to call this current, but really it's water particle velocities that is being accelerated vertically along the shaft of the structure of the wind turbine or the substation or whatever that is. Here is, and I've been kind enough not to put the name in, so I've just put in that this is a marine computational service. They put this in. This is approximately, or very accurately, 1.82 times what the OrcaFlex program would tell you. So now we are 2 times out, almost, of what the currents were. The real issue is what you see over on the right-hand side when we do the CFT, SST turbulence model for the thing is that the same freaking figures here, unfortunately, are very close to 7 meters per second. And those of you who played with mattresses and all kinds of things will know that anything you put out in the water with those kind of water speeds will flip, fly, wherever. The only thing that works is rock or rock filtered back of 8 tons. If somebody, and they have to be in minimum 3 stacked together. That's what's need to be there. That's the kind of forces that we have. This is the problem. This is what's causing it. The problem that we have now is, despite I love rock, I live in Bergen, I look down at the boats that leave Bergen full of rock, and that's nice. But the thing is, rock stabilization mitigates mobility, correct? But I've been working with dynamic cables for longer than I've been working with offshore wind. And the problem is, if you want to have something that's dynamic and you want to make this shorter and shorter distance that's dynamic, it's going to be worse and worse problem to make it work because the relative dynamics per millimeter of cable is going to increase through the roof. And this is the big problem. It increases the bending moment and strain, and it lowers the fatigue life of the cable. And that's quite dramatic. So if I'm going to compare this to dynamic cables, the typical thing that would happen with the dynamic cable when we did something like this was that we were going to be lucky if we got between 25 and 30% of the assumed lifetime out of the cable. So now the analysis that's been done that said, yes, it's good for 320 years, is suddenly going to tell you you're going to be lucky if this is going to last for 7, 8, 9 years. And this was the reason why the picture I showed you before, why the cable looked like a ragdoll after 2 years and 6 months in the sea. And this is not in a verse. This problem is going to be worse and worse because the areas that we are now developing wind parks in are more exposed. Yes, it's bigger turbines, but it's more surf areas. We have the issues around Taiwan, of course, all around APAC. We have the same problem in Eastern US, and I've been working on these projects, and I've been doing some of these CFT analysis of some of the projects, and they've been, unfortunately, coming out with the same results. That, yeah, we made a decision, but let's see what happens, because it's not a good one. So I believe that the rock berm principally is a good idea to stop the mobility on the seabed. The problem is that because it increases the stability, there's no soil spring feature which you will typically have when you engineer the CPS into the seabed. There's a soil spring, so you have a kind of a soft interface between the CPS in the sea, on the seabed, and getting into the seabed. This you don't have. This is the big problem. And I've seen, and you're probably not very interested, but I'm going to tell you anyway, the rock berm can look like this. On the top here on the right-hand side, you see the rock berm put on there. This is what would you call that, René? This small rock berm that we put here on top of the CPS system. Yeah, it's just, but this is the stabilizing. This is kind of thing. The problem is where I put the red arrow and where I actually just scissors in the OrcaFlex figure is, of course, this is the area where the water particles velocities are highest. This is the motor that creates the movement. So it's fine that the rock berm actually stabilizes the CPS under it, but of course there's a lot of movement in the interface into it. And generically, none of the CPSs today are designed to do it. Same thing on the bottom on a jacket. So I came up with this small new idea. That's the new idea I have, where I actually put something. I put down a dome on the seabed, and I put down the dome on the seabed that I can actually put it on top of the CPS, on an existing CPS, or for those who don't like CPSs, we can put it on a cable. Where we can actually have a reverse bending strain relief, for those of you who have read API 17. So we have a bending management system sitting down at the seabed that actually manage the curvaturing of the CPS in the interface into the seabed. Looks like this, a bit more. I'm not going to spend too much time on this. It can be put down with an RV. I'm not going to spend too much time on this either. I know that you're going to get the presentation in PDF format, so you can look at this and you can contact me more if you like it. But the thing is that we can actually install it on a new project. We can install it from the cable lay vessel. So here we can actually get this system installed, and we can install this without impacting the critical part of the cable lay vessel, because the cable lay vessel is going to have its RV sitting there for the approximately 30 minutes to 60 minutes between the CPS is interlocked till they actually have the temporary hang-off inside the tower made. This is the time that we're going to use to actually put these two pillows into the seabed. Looks like this. I just put this in so you can see it's flexing around. I must admit, I took some, I'm not an artist, but I took some artistic freedom. The wall thicknesses, and so you see here, are widely wrong. So this will be, in order to take this thing on for example, an HK set on Race Bank, just to name a few projects for no particular reason, the transversal forces on the CPS is in the region of 12.5 tons. Half of this is taken up by the interface into the foundation. Half of it has to be taken up by the seabed interface. When you put something down on the seabed scours away. So therefore, there's a little smart feature inside here where we can actually have a compression part in it, so it actually allows itself to drop down with the seabed. And as René has told us, never a problem with the scour protection, rocks and so around. But of course, nobody is interested in whether the rocks, they move around 10, 15 centimeters or something. But we are, when we have the CPS and the cable hooked up to it, then we need to be there. But the thing is, this is half a CPS, and it needs to be compressed against the between the seabed, against the scour protection on the left, and it can of course also be used on scour protected areas. I would say in most areas where people compete for price, you will only have non-scour protection around jackets, because I don't think anybody will want to pay for the extra 15 meters of monopiles. So, yeah. It gives a lot of freedom for the installation. You can put it around. There's one thing that I learned from working more than 30 years underwater, and one thing is it's nice being small underwater. I don't fit into that category possibly. But the other thing that's nice is there's nothing like small accuracies. I mean, if you come and ask, oh, we're going to put this down with 0.5 meter of accuracy, forget it. If you get 1.5 meter or something in a installation campaign, you're lucky. Very often we put out the monopiles, and often, now I've been told today in some of the projects they put the monopiles wrong. Often it's the other way around because they're being monitored by aerial systems. So the monopiles are put down accurately, but the scour protection may be off. That's it. I lost my time.
Then we're indeed a little bit over time, so I just have one question. Is the expected lifetime for that device 320 years or more?
The expected lifetime for that particular part is not the expected lifetime. And the cables are not expected lifetime. It's the fatigue life of it. There's a small difference there.
Okay, but so that's a no, is it?
Yeah.
Oh, but this is then also designed for retrofitting or only during?
It's both for retrofitting and for new set. But the thing is, some of the newer projects, they actually build in that they hope they will get extension on the leases, because the wind parks are so expensive that they expect that when after 40 years that they can actually get a 10-year extra. So, for example, Ørsted is asking for some of the projects for 40 years, not just 30 operational. Yeah.
Can I ask a question, please? Yeah, Henrik, thanks. That was a really good presentation and discussion. I'm Chris Sturgeon from Red Penguin. It seems to me that the real root cause is putting a static cable in a dynamic environment.
No.
But you're pinning it down. It's like a sticking plaster. You're trying to solve the problem with a cable protection system that repeatedly seems to be more of a cable failure system than a protection system. Sorry, is it not working? Well, I'll just follow then, because I'm probably quite loud. Thanks. Sorry, that's better. If I can finish. So, if you're putting a static cable in a dynamic environment, wherever, and then you put a protection system around it, you're increasing its surface area. So whether you call it current or you call it particle velocity, it's being exposed to forces. And by pinning it down, you're securing that part. But there are other parts still not, and you might have to put more and more stuff, whether it's rock placement, whether it's pinning and stabilization. You're trying to fix the problem rigidly. But if we put something in there that is more resilient to that environment and add to it the systems that you're talking about, would that not be better and provide a longer lifetime?
But imagine for yourself, what is a dynamic cable? A dynamic cable is a cable with some primary components, the three conductors, the fiber inside. That's principally not dynamic. So you need a package around it that can actually do the dynamics. And in most dynamic cables designs, what you do is that you actually design a dynamic package around it that allows a certain movement. And when the primary components see movement, that's the limit of the dynamics. So what we're doing here, or what I'm doing here with the system here, is that we actually put one dynamic, and it's not fixed. Yes, it's fixed deep into the seabed, but it's a bend stiffener. So it's a flexible thing that sits there that actually ensures that the bending curve of the cable is not so low that you will actually fatigue the cable. Each bend of a cable is a small, you come from a cable company. Each bend of a cable is a small damage to the cable. So if you're gentle enough, it will certainly work for 320 years, to answer your first question. If you're not, it will damage after 2.6 years, or even shorter.
Okay, good, thanks.
Okay.